as in the 1D problem, the finite dimensional weak form is the basis of our finite element formulation of the problem. Okay. Now, and of course, what we have to do is essentially define or construct the spaces that we need. We need to define SH and VH. Okay. In order to define these spaces, what we will do is construct a partition of our domain omega. Okay. So we define SH and VH by partitioning omega into subdomains omega sub E. Or I think we were working with an omega sup E actually, so let's just stick with that. Omega sup E. Okay, where E once again runs between 1 and NEL, right? NEL, as before, stands for number of elements in the partition. Okay, and furthermore, since each omega E is a subset of omega, which itself is a subset of R3, we are indeed talking of each element subdomain, omega E, as being a three-dimensional subdomain. Okay, so let me just draw the picture that we have in mind, and then we'll say more things about it. Okay, so this is omega, and what we are trying to say here is that we have, we're thinking of partitioning this subdomain, this domain omega into subdomains such as this one, and maybe another one right next to it, right, and so on, right, so, and maybe we'd call this one omega E1, we'd have omega E2, right, and so on. Okay, so mathematically, just as we had before, we see that omega each omega E really is open in R3, right? So we consider each of these, formally at least, to be an open subset, and therefore our total domain omega, which is the union of each omega E running from 1 to number of elements, right? And so, and you recall that as in the 1D problem, to make sure that we pick up all the interface points, right? The points at the interface between two of these element subdomains, we apply closure on the left and right. Okay, and that is an equality. All right, and of course we also know that omega E1 intersection omega E2 is the null set. Okay, so since each of them is open, their intersection is definitely a null set, right? Because we don't get any boundary points, right? But again, that's really a technical thing. We do indeed imply that they are non-overlapping elements, but what happens on their boundary is really a technical thing. Okay, so this is the setting. What we have to do now is talk about how we construct these subdomains, and once we do that, we will also be on our way to defining the underlying finite element basis. Okay, there are, of course, many ways to partition the domain omega into subdomains in 3 dimension. What we will start off with is actually not even the simplest such partition, but it is indeed the one that is most easy to get to given what we know about the 1D problem. Okay, and what that implies is that we are going to construct a partition where each omega e is what we call a hexahedral element. Okay, so consider hexahedral element subdomains omega e. All right, e going from 1 to NEL. Okay. So what we're talking of here is the following. We have this picture. We have one of these element subdomains, right? And I'm going to denote this one omega e. That is our total domain omega, right? So that's omega e, right? Now, in order to proceed with our finite element formulation, let's pull this element out of there, right? Look, let's examine it more closely. Okay. So that is our subdomain, right? This is omega e. Okay, the simplest case that we're going to start out looking at is where on this hexahedral element we are going to construct basis functions that are trilinear. Okay, so we will consider trilinear basis functions. Okay. Now, if we are talking of considering trilinear basis functions, what this implies is that we need to do this by introducing nodes over these hexahedral elements where we have one node at each vertex point of the hexahedral element and no more, right? No other nodes. So our nodes are at the hexahedral points, sorry, at the vertex points of the hexahedron. Okay, so we have There we go, right? So this means we have 8 nodes. Okay. So this, when we are going to work with trilinear basis functions, we have these element subdomains are sometimes also called 8-noded elements, right? They're sometimes called bricks, you know, very colloquial way of describing their construction. Okay. Okay, so that's the setting. Now, what we will do is, as before, we will denote coordinates for physical coordinates for each node. Okay, so if this so this is element omega e. Using the idea of local numbering of degrees of freedom and of nodes, let us suppose that this is node A for this element. Okay, so we are going to denote the coordinates of that point as x sub e sup A. Okay, and of course here A equals 1 through 8. Okay. Right. So where I have x A sub e, I'm going to say that this is local. This uses a local numbering of nodes. All right. Okay, and the numbering that's followed is actually we'll get to the numbering that's followed in just a little. Let's just stick with this now. All right. So if we have if we know that A runs over 1 through 8, let us then use that to write out our basis functions straight away. Okay. So now what we have is UH sub E, right? So that's UH in element E is the sum A going from 1 to number of nodes in the element, which we know, by the way, is 8, right? Because of the fact that we've chosen to construct trilinear basis functions. All right. With this, we have our basis functions, and we are going to use the same notation that we had before, right? These basis functions are in general written as being parameterized by physical position, right? X, by position in physical space X. And just as we had before, we are going to multiply them by degrees of freedom, dA sub E. And here too I'm using a local numbering of degrees of freedom, right? And this local numbering of degrees of freedom essentially reflects the local numbering of nodes. All right, we have this, and then we also have WH in element E is the sum A going from 1 to number of nodes in the element, NA function of physical position CAE. Okay. And at this point, things look very much the same as before, except for the fact that we have a much greater number of nodes. But we note that we know how these nodes are positioned, right? They're the vertices of a hexahedron. Okay. So now, if you think back to the way we proceeded in 1D, we took our physical element and regarded it as being obtained as through a mapping from a so-called parent domain. All right, we're going to do exactly the same here. Okay, so we will think of omega E as being obtained by a mapping from a parent domain. Again, we're going to denote that as omega sub c. All right. So having stated that, this is probably a good place to even stop this segment, because once we get into talking about the parent domain omega c, it is going to be just difficult to extract ourselves very quickly to end the segment. So we just pick up that definition in the following segment.